So I should say that my talk will be hopefully quite complementary, and will really cover our effort both in analog and also digital processing architecture based on atom arrays. And I would like to kind of look at that as kind of like opportunities, for both algorithms and architecture, co-design and optimization. So part of this work is basically a quest for controlling quantum world. And there are some big questions which we are trying to address. And it's essentially what we would like to do, would like to take some simple quantum objects and build more and more complex systems from them. And then with that, we hope to explore new physics, basically physics with engineered many-body systems, basically creating and probing new entangled states of matter. And actually in this domain, I would like to argue that we already kind of crossed the threshold of quantum advantage. There are basically the machines of the kind that I will talk to you about already were able to use to make true scientific discoveries, and these are discoveries which would be not possible to make if you just have classical simulators. But we also would like to, of course, start looking at kind of more general applications, and in particular ideas like quantum information processing. So I would say this, despite all of this excitement, this field faces two big questions. One of them is how to build truly large-scale quantum systems consisting of millions of quantum bits. And then the second question is how to apply them to achieve really useful advantage. So apart from this domain of quantum simulations, which I think is kind of special, this is really, a big challenge. And I think both of these efforts could really benefit from these ideas of, co-design and kind of optimization, as I hope you will see from my talk. Kind of at a high level, we now have in the labs systems involving different types of qubits, and they are capable both of analog and digital evolution. And the kind of the challenge of scaling up is really addressing these two contradictory requirements. One is controllability, which I think we perfected now with isolated few qubit systems. Another one is scalability, where we would like to really access and control large numbers of them. The current frontier is to really, do the tasks which modern classical computers cannot simulate, and that, to me involves, more over 100 qubit systems. And as already mentioned, that these systems are already being used to really make discoveries, to make really, to perform essentially scientific experiments, which you cannot simulate classically. But as you will see from my talk, we can also start using the systems to implement and test quantum algorithms. And if it's done kind of in the right way, with the appropriate co-design, we can really, push them into limits which are, kind of, I would say, kind of unprecedented. And, we could really try to make discoveries about what algorithms run well and what do not. And of course, another part is building bigger and better and in particular more useful quantum machines. So with this kind of high-level introduction, I will focus on this one specific approach, and this is building scalable quantum systems using Rydberg atom arrays. And in this approach, I will, within this approach, I would like to basically focus on two specific directions, two specific applications. One is of them involves analog dynamics, and this would involve use analog dynamics to test quantum optimization algorithms, and this will be done in a hardware efficient way using the co-design approach. And I will also talk to you about kind of a digital approach, which is based on a new architecture, which I think offers a lot of opportunities for both scaling up, but also it's particularly fruitful for this optimization and co-design and doing these things, which might enable us to experiment with logical qubits, and implement quantum algorithms with logical qubits in relatively near term. So in our approach, we literally build quantum systems atom by atom. And we do that starting with the laser-cooled neutral atoms and trap them using optical tweezers, tightly focused beams of light, which we use to grab individual atoms and hold them in place. So in our approach, we don't start with tweezers one at a time. We start, with hundreds, now thousands of tweezers, which where we try to trap atoms. And any given attempt, this trapping is not perfect. So we'll have basically some empty traps, some holes. And we are able to basically heal these imperfections, kind of remove these imperfections, literally by just taking a picture of atoms, figuring out which atoms are full and which are empty, and then basically kind of rearranging then the rest of the atoms in a way to create a defect-free arrays in a practically arbitrary configuration. So with that, we end up with atoms sitting, typically a couple of micrometers away from each other. So they do not interact at this point. To induce the interaction, what we do is we excite them into the Rydberg states. And that way, the atom size dramatically increases and they start talking to each other. And that way we can implement things like quantum logic or engineer the interactions. This is my joint project in collaboration between my group, the Marcus Greiner group at Harvard, and Vladan Vuletic at MIT. Just kind of a little bit of details, how we engineer this interaction. We use the so-called Rydberg atoms with large principal quantum numbers, and we like to use these atoms because they combine long lifetimes and strong interactions. So in particular for n equals 100, the van der Waals interactions of these atoms exceed those of the ground state atoms by 14 orders of magnitude. It's a big number, and we can make good use of these interactions. So in particular, one mechanism which we use is something which is called the Rydberg blockade, and this can be understood as follows. So basically, if you have two atoms and they are far away, and if you drive these atoms resonantly, then what you will do, you will just excite these atoms in Rydberg state and will undergo Rabi oscillations. But if you now bring these atoms together, at some point, this Rydberg interaction will take over, will become very large. And at this point, you will be able to excite one atom, either of these two atoms, but never both. And this is an essence of Rydberg blockade. Simultaneous excitation will be blocked at distances smaller than this blockade radius. And this is a mechanism which we actually like very much to use to entangle atoms. The reason is that at this point, this mechanism is very robust. It's insensitive to exact position between the atoms. It's insensitive to things like atomic motion. So altogether, in what follows, I will use the following approach, where we will basically start with some kind of set of atoms. We will rearrange them to create a desired configuration, and then we will subject them to laser pulses, which will either change the hyperfine states or excite them in the Rydberg state, and then at the end we'll do a projective readout. So that's a kind of the overall approach within this architecture. So within this general approach are, of course, a lot of practical aspects. And one kind of general question is, which atom do you choose? There are, I will focus in particular on rubidium atoms as an alkali atom, like hydrogen-like atom. But you can also choose other atoms like alkaline earth, like strontium or ytterbium. They kind of to the leading order, they are very similar, but they have different features. And these features can be exploited if you want, for example, to kind of specifically optimize certain aspect of your approach. Then there is also a choice of encoding. So even within a given atom, and as I said, we'll focus here on rubidium, you can either choose to encode qubits in a superposition of ground and Rydberg states, or alternatively encode the qubit in hyperfine states, basically spin states of atoms, and the advantage here is that the spin states of atoms are basically non-interacting. They have very long lifetime, and just only when you need them to interact to execute the gate, you would excite this atom into the Rydberg state. So in what follows, I will show you two examples involving both of these approaches. So as I already mentioned, one could apply this architecture both in the sense of analog and digital fashion, but there is one kind of very natural implementation, and it is literally corresponds to implementing the original vision that Feynman had, 40 years ago, over 40 years ago, when he started thinking about quantum computers. And that's the idea of programmable quantum simulator. So to kind of understand this, let's consider first this one-dimensional chain of the atoms, like it's shown here. Suppose that atoms are equally distantly spaced. And let's encode qubits in ground and Rydberg states. So in this case, you can write down the Hamiltonian, which will describe the interaction. So let's assume that we excite these atoms homogeneously. So there will be a Rabi excitation term. There will be this detuning term, which corresponds to the chemical potential. So n is the number of Rydberg atom on each lattice site. And then this is the interaction. So to kind of understand what type of processes we can study with this Hamiltonian, we can just look at the phase diagram, which of the ground state phase diagram, which corresponds, which is spanned by this interaction range and the detuning. And so if atoms are not interacting, then depending on the sign of detuning, you would like to have either all atoms in the ground state or all atoms in the excited state. But when this detuning is finite, what will happen is that, of course, the state like this, where you excite all Rydberg atoms, will not be accessible. So if, for example, you are blocked only within kind of nearest neighbors range, then you should be able to excite half of the atoms, basically every other atom. So this will be the state which is accessible. So it's a state as an antiferromagnetic order. So it's up, down, up, down, up, down state. And if you now increase the interaction range even further, then you will be able to excite every third atom and every fourth atom and so on. And so basically, this is the kind of within our system, we can explore this phase diagram very easily by, for example, starting with all atoms in the ground state, starting with detuning in the negative region, where this ground state is an eigenstate, and then just do adiabatic sweeps to kind of enter all of these different states, and this is some of our first experimental data which we obtained on this system. So clearly here you basically start with all atoms in the ground state with a chain, and then you go into a state where every other atom is excited. And you basically, what you see here is a kind of a snapshots of quantum phase transition, where system orders, and in the process of ordering, different states compete with each other and so on. And you can, in this case, by just bringing atoms closer, you can block not only the first but second nearest neighbor, and you can create this state with Z3 symmetry broken and this Z4 symmetry broken. So basically, all of these states you can explore by just programming the interaction, by positioning the atoms, by choosing which state you will excite, and things, and doing things like this. Now, last 2.5 years, we operated what we call generation 3 of the atom array, which was enabled by this simple device called the special light modulator, which is basically a computer-generated hologram, where you can basically create within 2D kind of an arbitrary pattern of laser beams. And if you project it inside the vacuum chamber, in this case, you have array over thousands of traps. So this is an amazing device, SLM, but one disadvantage is relatively slow. So to actually move atoms within this traps, what we do, we use 2 acousto-optic deflectors. So these are basically the devices where you can input a sound, and for each tone of the sound, you deflect the laser beam. And in practice, we use 2 of them to basically move columns and rows of atoms. And so everything is computer controlled. And one last thing which happened, and it's probably why our workshop is still online, is that, of course, it was a pandemic. So this is actually kind of a historical picture where, this is basically a loss. We had to shut down our lab, but we were told that, we can let the servers operate, and we had 1 week warning. So during this 1 week, this experiment became a server. So you see these people on the last day when we were all allowed to be in the lab, and these people are very tired but happy. So the situation developed successfully. So basically since when we almost exclusively run this experiment remotely. So we are now completing generation 3 upgrade. So fingers crossed, nothing like this happens again. So, but basically. In this generation 2, what we create is create large scale, basically 2D arrays. with system sizes up to about 300 atoms. And so these are with different ordered lattices, so here is an arbitrary pattern. This will be important actually in the following part of my talk. So this is, for example, you program, where atoms should be sitting, you press a button and, you see the atoms. So, and basically, as I said, we kind of, start with about 600 traps filled with a little more than 50%. So we have about, 300 sorted atoms. So what one can do with that is, for example, one can immediately extend these things which I told you about in 1D to 2 dimensions. So we can explore, for example, quantum phase transitions in 2-dimensional arrays. And the way how you do it, you just adjust blockade radius to control interaction range and then do adiabatic sweep. So starting from atoms in the ground state, if you go across a phase transition, here is a picture of perfect anti-ferromagnetic pattern across the entire array. So this is not what you see in every shot of experiment. So in general, you see some kind of defect. So you need to evaluate, some kind of statistical quantities, like, for example, correlation functions. You can also look at things microscopically and ask what's the probability that this kind of state will appear. So actually, it turns out that this state and the state shift where the pattern is shifted by lattice side away, although not very probable, still is the most probable from all microscopic configurations. And this probability actually decreases exponentially, but this scaling law is 0.97 to the power of n. This means that there is a 3% error per atom, but it includes everything: imperfect preparation, quantum fluctuations, finite speed, and stuff like that. And as already mentioned by Fred, kind of one of the most interesting things about the systems is to study their dynamics. And if you go dynamically, for example, across the array, what you can do, you can watch how this typical correlation lengths grow. And this actually allows one to, for example, extract what's called critical exponents of this transition. In fact, it allows us to verify what we are doing is really a quantum phase transition rather than classical, because these critical exponents are very special and they're distinct for quantum phase transition in 2 dimensions, classical phase transition in 2 dimensions, the boundary-driven transitions, and these are the kinds of things we can study. So basically, with this kind of systems over the last 2.5 years, we had a lot of fun, and we explored a wide variety of different applications. Most of them was in the domain of quantum simulations. So, for example, we studied exotic phase diagrams in 2 dimensions of different phases. We also took the system far away from equilibrium. And this is, something where we actually really made the first discovery. So that's this idea of quantum many-body scalar. It's a phenomenon which we discovered in a lab, and there is a lot of theoretical work understanding it. So one other important milestone was the realization of first realization of topological spin liquid. This is a state of matter which has been basically proposed, by Anderson nearly 50 years ago, and actually has not been created in a lab up to now. And this is, what we were able to do. This is related to ideas of topological quantum computing and things like this. There is also important non-equilibrium aspect of that. There is another discovery that we made with that. So basically, in that kind of sense, in the terms of like scientific applications, understanding strongly correlated matter, and in particular its dynamics, I would say these systems are already in the domain of quantum advantage. So I'll talk to you about 2 topics which are sort of more in the quantum computing realm. One of them involving exploring combinatorial optimization, and another one is kind of more universal, going towards universal large-scale machine. But I should say that the machine similar to the one which I have already described is also something that we have kind of built in our startup company. So there are basically now more than 1 machine in town here. And actually, this is a Quera computing. And actually, this Quera machine will be available on AWS Bracket cloud, very soon. So stay tuned. And basically, this is actually kind of a bit of a milestone, because this is actually a very complex systems, which up to just up to basically 2020, no one was able to operate remotely in any setting, and the fact that, this kind of, system will be available to public, is kind of a bit of a miracle, technical miracle, I would say. But anyway, so what I'll do now is I'll focus on two recent examples where the ideas of co-designing algorithms which are, particularly suitable to these hardware platforms really, paid off and will pay off even more in the future. So the first application I will describe will involve the combinatorial optimization. And in particular, I will focus on one specific problem, which is called maximum independence set. So this is actually a relatively simple problem, but it's hard to solve. And this problem essentially is a graph problem. It involves vertices which are connected by edges. And the independent set is the set of vertices which are not directly connected by edges. So in other words, kind of in simple ways, the goal of maximum independent set is to basically try to color some vertices, but you cannot color vertices which are directly connected. And maximum independence set is to find the maximal number of vertices which you can actually color. So what's shown here is an example of this maximum independent set on a so-called unit disk graph. So basically the situation where every two vertices within given distance are directly connected with each other. Actually, if you look at it and kind of, basically kind of imagine that this workshop would be real and not virtual. And, this is something that we would all see in this kind of on the back page of the airline magazine. So it's kind of, you clearly see that this problem has, real world connections. And indeed, it turns out that, there are many real world applications, for example, in designing network, machine learning, and so on. But actually this, even on this kind of unit disk specific setting, this is an example of a complete problem. To find the exact solution of this problem is actually hard. So at the same time, if you followed my talk up to now, what you will realize is that this kind of problem has a lot of connections with Rydberg blockade. Remember, in Rydberg blockade, we tried to excite as many atoms as possible, but we could not excite atoms which are sitting within blockade radius. And that actually mathematically turns out to be, correct. So in fact, the cost function of the classical kind of cost function of this problem corresponds to classical cost function of the Rydberg Hamiltonian. So basically there is this detuning term, which you would like to make positive to maximize the number of Rydberg atoms, or in other words, maximize the number of vertices you can color, but you will not be able to color any vertices which are sitting within blockade radius. And so basically this kind of realization, which is, due to Hannes Pichler and co-authors a few years ago, basically enabled us to kind of test the quantum optimization algorithms using the Rydberg platform, I would say, in a somewhat kind of unprecedented regime. So, of course, solving these optimization problems and accelerating them and using quantum machines is a very active research direction, and there is a lot of theoretical work. There is also work on the D-wave machine. But the key question here is that can you actually test these algorithms going beyond the so-called shallow circuit depths? And so the way how to do it in our case, the answer to that is basically to use co-design. So essentially, what happens here is that we can encode MIS on unit disk using this Rydberg blockade idea in a kind of super hardware efficient fashion. So in particular, let's consider this graph like it's shown here. And basically in this graph, every vertex corresponds to a single atom. And we adjust the blockade radius to give us basically kind of a unit disk condition. And afterwards, to solve this problem, what we start doing is we basically excite all of these atoms with the laser, and we try to basically optimize our excitation such that we actually can excite as many atoms as possible, but subject to the blockade constraint. And basically, by definition, this should give us the solution. If we can really do it optimally, perfectly, it should give us a solution to the maximum independence set problem. So in practice, what we do is we actually explore a family of variational algorithms, and which are parameterized in some way, and we actually use the kind of closed loop optimization procedure. So in this kind of closed loop optimization, you can ask for different kind of metrics. So the figures of merit which we use is our approximation ratio, which is basically mean size of independent size divided by size of actual MIS, or alternatively, the probability to actually find an MIS, in a given sort of, run. And basically, the way how we explore these algorithms is essentially we take this platform, parameterize our pulses, and essentially, apply it to, set of, hundreds of thousands of different graphs. And in fact, that's what we have done under DARPA ONISC program. So basically, these results, on hundreds of graphs, kind of both in terms of, approximation ratio, but also in this probability to find MIS. And what you see here is what, for example, even for graphs of a similar size, there are basically several orders of magnitude in terms of performance, which different graphs span. So basically, what it means is that, not all graphs are the same. There are hard graphs which are easy, and there are graphs which are very hard. So I'm not going to go into details. I'm happy to discuss this, but there are just two aspects which I would like to highlight. So one of them is that we tried to use different types of algorithms. So one of them is this quantum approximate optimization algorithm, and and it performed kind of okay. So we were able to push it to a depth of 4 or 5 with some improvement. But actually, it turns out that these kind of results are, completely outperformed by doing, optimized quasi-adiabatic algorithm. So basically, where we design the system such that it kind of deliberately doesn't come too far away from the ground state during the entire evolution. So, and in fact, the effective depth we can achieve with some improvements, for this quasi-adiabatic algorithm, which actually is something like 32, corresponding to the number of qubits times the effective depth product over 2000. And this actually is enabled also by using stochastic optimized, which is designed by our Quera colleagues. So, okay, so the only maybe one aspect which I would like to now discuss is related to benchmarking of this algorithm. So basically, to understand how well this quantum algorithm perform, we actually picked simulated annealing, which is kind of a general purpose classical algorithm, and essentially it turns out it applies to our algorithm family. And in the simulated annealing, as most of you know, basically what you do is just classically cool to the Hamiltonian ground state by stochastically flipping spins. And it turns, and we can just now take instances and compare them directly, in a quantum machine and simulated annealing. So actually, in our work, we've optimized simulated annealing using collective updates to actually find the optimal performance. And here is kind of one sampling of the results. So here is, we're looking at the kind of 1 minus approximation ratio. And there are two regimes in which we can see. So by the way, so the lines are simulated annealing and dots are experiment. So there are two regimes. One is a kind of high temperature regime or high energy regime, where you see that all of these lines for different things and different colors correspond to different graphs, basically are roughly parallel to each other. But then, and like it kind of makes sense, hard instances classically, also hard quantum mechanically. But then something interesting happens in the regime of low energies. And what you see here is that in some of the instances, the classical algorithm really gets stuck. And it evidently gets stuck in some local minima. It finds some solution, which is pretty good, but not really perfect. And so it turns out that, we can actually understand why this happens. So it's basically, these are the instances where the problem has a lot of pretty good solutions, but few actual perfect solutions. And so at this point, the simulated annealing, what it does, it basically just performs a random work on this hypergraph, in this case for solutions which size is MIS -1. And only when it comes to the very close to the edge, which can lead to MIS, it actually would make this kind of transition. So it turns out that this is actually a fundamental limit. One can prove it, and it's characterized by a hardness parameter, which is a number of MIS -1 divided by the number of edges leading to MIS, which actually scales exponentially with the system size. Now, what we do is having realized that, we pick the instances which are actually hard for classical algorithm. And again, we pick a number of them and throw them both to the quantum and the classical machine. And here are some results. So we find that in some instances, basically, which are hard classically, the quantum machine just solves them. In some other instances, basically quantum machine also gets stuck. And again, it's very hard to see this from just two. So what you need to do, you need to generate, something in order of hundreds of instances. So this is performance at a certain depth. And what you see is that, for many instances, quantum machine really outperforms the classical machine, but not for all. In some instances, classical simulated annealing is better than the quantum machine. So the question now is, what controls the quantum hardness? And maybe not very surprisingly, we found that the quantum hardness is controlled by a minimum energy gap. So the way how we are able to show it is we run some instances which are sufficiently small where we can actually do the calculation, where we know the energy spectrum. And what we found is that basically the kind of optimized quasi-adiabatic trajectory gave best results when this optimization allowed it to slow down right at the point where the minimum gap is achieved. So basically, it's kind of a proof that the minimum gap is what determines its performance. Moreover, we can also look at the probability to find maximum independent set as a function of minimum gap. And what we see is that for many points, we have this near kind of perfect Landau-Zinner scaling, which basically, really an indication of that the hardness is controlled by the adiabatic gap. But again, this happens for many instances, but not all. So there are some instances where this, probability is not correlated at all with the minimum gap. And actually, it turns out these are the instances where essentially our circuit was not sufficiently deep, is not deep enough. So, so we are kind of basically exceeding speed limit for these instances. And actually, we can now look and reanalyze our data. So basically, what we see is that if we look at all instances, the quantum and classical scaling kind of look very similar to each other. But if we only look the instances where in a deep circuit regime, where basically we can go to sufficiently large depths that the algorithm sees the entire graph. So in this case, we see a superlinear kind of nearly quadratic speedup. And I would like to emphasize that, this only occurs, in a regime where we have an effective kind of n times the circuit depth is actually more than 2500. So these kind of near-term systems really allow us to explore these regimes when we kind of design our algorithms appropriately. So kind of motivated by these findings, our current effort involves exploring, questions like, can we show that we can provable speed up for all maybe classes of instances? Can we find instances which are faster than quadratic speedup? And we're also exploring scaling up involving understanding and controlling errors. So I just give you a little bit of kind of insight into ongoing work. So one kind of direction is to really see whether we can actually obtain a provable quadratic speedup. And it turns out that it's possible under the conditions where you can actually prepare the states where in this kind of solution space of kind of, pretty good solutions, but not perfect solutions, you can really kind of create these delocalized states. And actually it turns out that it's possible to engineer them by engineer the Hamiltonian appropriately. And in these cases, you can basically prove that you will have a Grover-like speedup for these instances, as kind of indicated here. This speed up is actually involves comparison of quantum algorithms with a broad class of classical algorithms, not just simulated annealing, but also quantum Monte Carlo, parallel tempering. All of them basically, all of them would fall under this class where we can have a Grover quantum speed up on them for these classes of hard graphs. One other thing which we sort of discovered by kind of reanalyzing our data is that there are some instances here, for example, which perform extremely well, which are pretty hard. And so basically, it again happens for very deep circuits, but for these instances, it turns out that like in a solution space, the wave function is actually not delocalized. In fact, it is here localized, but it's actually localized in a kind of favorable way. It's actually localized close to these edges which lead to the MIS. And actually this gives us maybe some clues that maybe there are some instances where you can have some enhanced gap and actually maybe better than Grover speed up potentially with this kind of Rydberg Hamiltonian. And this is something which we are exploring now. We're also interested to go beyond the unit disk graphs. And again, we utilize this idea of co-design here. The key here is to kind of develop, certain types of gadgets which can basically encode complex non-unit disk problems using these gadgets into the unit disk Rydberg Hamiltonian. And basically, the kind of fundamental idea is that you can basically construct this non-local connectivity by just introducing additional ancilla atoms and basically utilizing the fact that they kind of order. And basically, essentially, it turns out that you can encode any arbitrary instance into the kind of lattice which I just showed you with at most quadratic overhead. And in fact, we kind of showed that one can make encode maximum independent set with non-unit disk graphs, Kubo Ising problems, but even things like integer factoring you can encode. And what you see here is kind of an atom arrangements which allow you to do it. So there is a lot of kind of potential in terms of really kind of implementing these techniques, and this is something that we work on together with Hannes Pichler and our collaborators at Quera Computing. So in this last 10 or so minutes, I would like to switch gears a little bit and talk about digital quantum processing. And again, what I would like to do, I'd like to focus kind of on a new architecture here, which will utilize this kind of the ability to kind of move atoms and rearrange them at will. But instead of what I've shown you here, where we basically first kind of design the atomic system with certain connectivity and try to basically then run our algorithm, I will focus on the architecture in which this connectivity is itself kind of a living organism, can change during basically the program which we are running. And the idea here is to basically encode qubits into the long-lived states, for example, spin states, hyperfine states of the atoms, So in this states, basically the qubit lifetime is limited by quality of vacuum. Right now it's about 3 seconds, but it can be easily minutes. And only when we need to execute, for example, gate operations, we excite this one of the states into the Rydberg states. And the beauty is, once you do this kind of encoding, it turns out that you can just move the atoms around while preserving the coherence, while keeping, the quantum states intact. So here is a demonstration. So let's consider the situation where we started with pairs of atoms, and then we entangle them using controlled phase operation, which is actually, can be done very effectively. It's kind of our native operation, if you want. And you can check that you have entanglement by using, for example, a 2-atom parity signal. But then instead of that, just measuring in situ, what you could do, you could just take these entangled pairs and move them apart from atoms, apart from each other, and then check the entanglement here again. And actually, what you see here is that basically the entanglement has been completely preserved. So coherence and entanglement are perfectly preserved in this case. So this gives rise to this idea of a new architecture where basically you start with certain qubits located at certain spots which have certain connectivity. You can execute certain gate operations, but then instead of keeping this connectivity fixed, what you do, you just move the atoms around, and that's, kind of creates quite a unique architecture where, connectivity is itself kind of a living organism. So with that approach, there are a lot of cool opportunities, and some we're already explored, some are exploring. So for example, we were able to generate very efficiently, 1D cluster states. We can also, for example, create states, associated with like steam code or correcting codes. So something that I will actually focus on a little bit is basically surface and toric codes. And actually, within this approach, you can also explore this very exotic analog digital architecture where you can interrupt the periods of analog evolution with some digital operation and continue the analog evolution, maybe possibly with a different connectivity. So let me just focus on this approach very briefly. And in fact, what I would like to do is, how about, we try to implement a toric code on a torus. That seems kind of hard in two-dimensional system, but we can do it. And just to explain what we are doing, so just very quick correction primer, as you all know, quantum error correction code, you would like to start with a grid of physical qubits, which will encode logical qubits, and which will be building blocks for fault-tolerant quantum computing. And then you use this kind of extra qubits, which are called ancillas, to do stabilizer measurement to detect the local errors. So this is one way how one could, in principle, think to implement toric code on a torus. So red qubits here are ancilla, the black data qubits, but actually that seems hard on two-dimensional architecture. How would you do it? Well, so it turns out that this toric code is equivalent to a graph state with non-local connectivity. So basically, if you sort of somehow can design wires which will connect these ancilla qubits to these qubits also on the other side of the system, or these ancilla qubits, on the top of the system, then you can actually do this kind of local parity check. You can create you can create logical states. So in order to implement this, we actually looked at the old idea, which actually is due to Peter Zoller and Ignacio Chirac. It's actually one of the very few ideas of them which has not been implemented up to now. So at the time, around 2000, people were still thinking about, the magnetic hard drives, so people thought, what would be a quantum analog of magnetic hard drive? And then they kind of thought about this, some kind of quantum head, which would go around and interact with arrays of ions or atoms. So we implemented this idea, but instead of just one qubit in this quantum head, what we do is we utilize the array of 8 ancillas. So here is a movie which shows how we actually created a toric code on a torus. So there are 16 data qubits and there are 8 ancillas moving. So each of these red things here is a controlled phase operation, and then we move the ancilla into the kind of readout zone. So how do we verify that we actually created an error correcting code? So in this case, it's a Tori code on a torus. You can encode 2 logical qubits. In fact, these are characterized by the stabilizers. In this case, we want to prepare like X, the kind of X, both qubits in X state. So they are basically stabilizers, measurements of products of X operators going one way or the other. And in fact, we can measure these things directly. So we can have raw measurements, which are, which show there are some signals, but we of course have access to all stabilizers. So we can do kind of error correction, or in this case, it's just a single round, basically error detection. Now what you see, one of these qubits, you can, stabilize to basically kind of, all the way to 1. The other one is not as well protected, but still this works. So, there are clearly new exciting opportunities, to do various types of encoding. So things like, for example, hypergraph codes or DPC codes is something which we're actively exploring. So we also have a pretty good understanding of the types of errors which we have. And in fact, we and also other groups started looking at hardware efficient methods for quantum error correction. So this architecture is also very suitable for measurement-based quantum computing, which we are kind of looking at, both in 2 and higher spatial dimensions. And there are, of course, these hybrid approaches that I already mentioned. But just to give you a little bit of feeling, there are kind of a couple of directions. One of them involving basically processing quantum information using logical qubits. And the key idea in our case is a very high degree of parallelism. So for example, if we have quantum information encoded in blocks, we can basically certainly do a single qubit Clifford gates, but with high degree of parallelism, but also do a 2 qubit logic operation just by bringing these codes blocks together and doing gates in parallel. And this really is kind of an exciting opportunity in terms of control. We can really think about single logical qubit control instead of single physical qubit control. And this actually allows us for multiplexing, which is very, very natural using optical techniques. So this approach is also a very fruitful ground for kind of optimization and, and kind of synthesis. And, a couple of months ago, Jason Kong, who will be here in a panel, saw some of the talks from our group members, and he immediately recognized that this is a very, very special opportunity. And what one could do is one could now think about really optimizing this architecture by using certain variables and certain constraints, and really try to solve the problem where you really optimize how you can implement of a certain specific algorithm. So here is just a toy example, is a simple QA program, which Jason and his group has explored. So I mean, the reason why I think they did it is because they kind of had some experience of that, looking at the Google Sycamore processor. So to implement a program like this on Sycamore, we need a certain number of swap operators. But in our case, this is not needed. So basically here is kind of a optimal solution that they came up with, which basically involves moving, certain subset of atoms, basically using the techniques which we already have in place. And by basically kind of implementing this algorithm, with basically 0 swaps. And, you can immediately see the gain, both in terms of the gate count, but also in terms of fidelities. And I think there is a lot of room for improvement. And I think we are both, our group and also Jason's, are very excited about, kind of deploying the tools that, he and his team has developed. I would like to kind of, maybe zoom out a little bit and, mention that there are many exciting opportunities which we are pursuing now in the lab. So one of them is developing techniques for kind of independent control. We like to think about control in terms of channels. And, we already have tools to control, something on the order of like 30 or so channels. We're developing tools to control thousands of channels. We are looking on optimizing the architecture, in particular improving fidelity of our gates. So our single qubit gates are actually very, very good. With errors less than 10 to the minus 4. And there's a lot of room for improvement. Our main limitation is actually 2 qubit operations, which when implemented in parallel up to now has about a % level error per gate. But we're also looking at the new approaches to do some hardware efficient error correction, utilizing the types of errors which we have. We start to look at optimal layout, and also start thinking about, again, combining these two directions for the given algorithm. What would be the optimal architecture? What would be the optimal approach? So we are looking also at the modular approaches, and also, as I already mentioned, the device kind of more related to the first part of my talk will be actually available on a cloud very soon. So we look forward to people to kind of use it, and for a community to access it and do science with that. So I hope I convinced you that this is really an exciting scientific frontier, and there is a lot of opportunities for new architectures, co-design and optimization, involving both near-term quantum algorithm tests, but also advising a longer-term, basically, quantum processing with the logical qubits. So with that, I would like to thank you for your attention, and also thank all these people, whose blood and sweat resulted in this work. Thank you very much.